Talk of this session is Matthew Parkinson from Microsoft, as your research, as it's now called. And he's going to tell us about weight-free weak reference counting.
Cool. So thank you very much for the invitation to talk here. It's a great honour. So I found this picture on the internet of Pete's office, and I remember as a PhD student going for the first time there when I had some ideas about separation logic and being very nervous about turning up and sort of presenting to all these people. And within about a year of doing that, I would go down very regularly and I wouldn't be at all nervous, and it was an amazing place to go. And I learned so much stuff there about concurrency, automation, all these things that I had no idea, like memory management. It was amazing. And this talk is some recent research I've done, which kind of pulls together many of the things I learned staring at this whiteboard and talking to very, very many people in Pete's office. So let me begin by explaining the title. So, weight-free weak reference counting. So let's start with the end. So what's reference counting? So in this audience, hopefully people know about memory management. So reference counting is keeping track of the number of incoming edges to an object by a count. And when that count reaches 0, we can collect the object. So super simple example here. We've got a graph, sort of a tree with a couple of references coming into it. If we remove that top reference, the reference count goes down, the object at the top can go away, and we can collect it. And then the next object in the tree can go away as well. Awesome. This is nice and simple. Well, one of the problems with reference counting is cycles. So if you have reference counting and you have cycles, then you have an inability to collect some objects. So let's take the same graph, but now instead of it being a tree, it's a parent pointing tree, because obviously you want parent pointers when you do various algorithms. So now we've got references to that top node from the subnodes. So if we take away that reference count going into the top, the reference count goes down to 2. And maybe we take the other reference count down to the tree. And now, well, all of these things have a reference count. It's a perfectly sensible thing to do, and the memory doesn't get collected. So in the sort of reference counting literature, there's things called weak references. So these are basically references that keep the object alive, but not really. So you kind of break down the idea of deallocating an object into, I can run the destructor and I can reclaim the memory. And running the destructor is when the strong reference count reaches 0, and actually reclaiming the memory is when the weak reference count reaches 0. This is nice and simple. So if we take this graph now, if we make all our parent pointers weak, then actually we can start to reclaim stuff. So if we drop that top reference again, the strong reference count goes down to 0, the weak reference count remains as 2. But that means we can run the destructor. So that means its outgoing edges go away. So those strong reference counts go down, and then that right-hand object can be reclaimed. Now the top one can't, because it's still got a weak reference count, because there's still potential for someone to try and reference count it, but at least its destructor's run and the things it can reach can go away. So it's kind of annoying that can't be deallocated, but it also we can't get a strong reference count back. So but once you've reached strong reference count 0, you can't get a new weak reference. From a weak reference count, you can't get a strong reference. So this final part of the title was weight-free. So this is something I definitely learned staring at that whiteboard. So there's a whole spectrum of things in the concurrency world about progress properties. So there's kind of, on one end of your spectrum, you've got blocking, which is where you take locks and you've got no potential for progress. If a thread goes away for a while, nothing can make progress because it's holding a lock potentially. And then you kind of gradually build up more and more progress properties. So you've got obstruction freedom that lets some stuff make progress. If you stop, then if everyone stops, then something can make progress, and lock free is a bit stronger. And weight free is like the best. So weight free it actually works. Like it terminates, right? Independent of what anyone else is doing. So if we want to look at this title, what we're going to do is build a weight-free version of weak reference counting. So was it not weight-free to start with? Well, let's have a look at the state machine underlying what's going on with reference counting. So you have strong reference counts, and you can increment them, and you can decrement them. And when you hit strong reference count 0, you have to run the destructor. So you can't move out of strong 0 to strong 1, because once you hit 0, you have to stop there. So this 0 to 1 transition shouldn't exist. Now, the Incref, if I have a strong reference count, can be implemented just with an atomic operation of incrementing. And the decref can be implemented just by an atomic operation of decrementing. But if I only have a weak reference count, I don't know if I'm in this strong zero state. So, sorry, there's a bit there. So to actually implement this, we need a CAS loop. So what is going to happen in your, like if you read the C++ standard library or you read the Rust standard library, what they do is they read the value in the strong reference count, then try to increment it with a CAS. If you try to increment it with a CAS, that isn't weight-free, because something could come along between the point where you read it, here, and the point where you do your CAS, and then that can make you go back and try again, and try again, and try again. So your classic operation for doing promotion from weak reference to strong reference in weak reference to strong reference isn't weight-free. It's lock-free, but it's not weight-free. So can we do better? And is this a problem? Well, if you run a really tight loop, create a micro benchmark, because if you want to prove any point you want, you can find the right micro benchmark for that, because there's always a micro benchmark that tells you the performance thing you want. And here's the one I wanted. So this is basically a really tight loop doing a weak reference to strong reference promotion. And what happens is you see that it gets really bad quickly, and it gets worse and worse the more threads we have. In particular, there's an inflection point here when we hit the hyperthreading limit of the machine, and it starts to really contend with itself. So there's lots of contention going on, and it basically manages to shoot itself in the foot, and it goes slower and slower and slower. So how can we build an algorithm that doesn't have this problem? So this is the solution time. So here we've got the same strong reference count kind of state machine. So we've got strong 0, strong 1. And what we're going to do is add this edge back in. So we're going to allow you to increment away from strong 0. So what this means is you can reach strong 0 multiple times. So one thing that I forgot to say in the previous bit was when you go from strong 1 to strong 0, you effectively get a weak reference count given to you. So that weak reference count says you can now go and run the destructor, and you can kind of know the object's going to exist still for a while, so you can do your stuff. And then what's going to happen here is if we go back, we have to give back that weak reference count, and this is really important to get the algorithm right. And some of you in the audience might say, is this ownership transfer? It is. It's ownership transfer, right? When you do this, you're basically taking out from an invariant a weak reference count and putting it back in. So when you're moving through this state machine, you're doing ownership transfer. And the way we can then make this work is to make actually hitting that point where we should do the destructor a two-stage operation. So we hit strong 0, and then we attempt to close it. So being strong 0 isn't enough to say there are no reference counts. We have an extra state, which is close, which we can move to. And so really importantly, if we didn't have this, oh, you can't see my cursor. If we didn't have this kind of add back the weak reference count, the algorithm's wrong. And I didn't know this so we have a paper at ISMM last year on this. But there's actually a paper the year before at PLDI that did something very similar and doesn't have this edge and is actually unsound. Which would have been great to know when I wrote the ISMM paper. It would have been much easier to get it accepted, but sometimes you don't. So how can we represent this? Well, we can do this really easily by saying that closing is basically, this closed state is any odd number. And the strong reference count is an even number, the reference count times 2. So if we do that now, incref, if I basically add 2, it moves me through the strong counts. So that's an atomic operation I get on most processors, adding 2. And decrementing 2 is an operation I get on most processors as well. So I can do the inc twice, add 2 and subtract 2, and they're weight-free guaranteed by the processor. And the closed is a CAS, but I only have to try and turn it from 0 to 1. And if I CAS from 0 to 1 and I fail, well, that means it isn't strong 0 and someone's come in and done an incref at the same time. So I have, so I think that's atomically subtract. I think I said all those without this slide. So, cool. Plenty of time, I'll slow down. So you might look at this and think, this is getting very complicated. And you might want to ask, can you verify this algorithm? Well, yes, we can, Pete. So we've got a Starling verification. So this is a tool that Matt Windsor, who's a PhD student of Mike Dodd's at York, wrote a few years back, but uses kind of the views framework, so the concurrency stuff that Philippa and Thomas and I and Lars and Hong Sok did, and builds a kind of decision procedure from it. So with that technique, we can then build a way of actually verifying that thing. So here's kind of roughly what the proof looks like. So it's written in C++ code, although Starling has some weird internal language that Matt Windsor built, but it's very nice, but isn't C++ code. So when you enter release strong, effectively what you have is a strong reference, and then we're going to subtract 2. So if we want to subtract 2, and if that wasn't 2 when we did it, then we're going to carry on. Otherwise, we've succeeded. We've moved from, say, strong 1 to strong 2 to strong 1, or strong 3 to strong 2, etc. But we haven't moved from strong 1 to strong 0. If we have moved from strong 1 to strong 0, then we should get a weak reference out. So that's part of the way the Starling proof works. It gives us this weak reference, but we can actually now use to carry on accessing the object, because we know it's not going to be deallocated. And then we try to do this crazy thing of turning it from 0 to 1. So this is closing it. And what that means is if we succeed in closing it, then we get this destruct permission, and if otherwise we have the weak reference. And if we do have the destruct permission, then we can run the destructor, and when we run the destructor, we get back our weak reference, and when we do that, otherwise we've got a weak reference from not failing to close it, and then we release the weak reference. And this all goes through in Starling quite nicely, with a lot of meaning of what those definitions are. And then the acquire strong from weak does the kind of the other side of this. So you start with a weak reference, you add 2. If you added 2 and the result is even, then you've got a strong reference. Cool, that's good. We can exit and which way am I trying? Acquire strong from weak. So if it's not 2, we failed. So if it's not even, we've failed to do it, so we just give back the weak reference. If we did succeed in the increment, we need to check one more thing, which is, did we move ourselves away from strong 0 to strong 1? So if the previous value of old was 0, then we actually have to go and create a new weak reference. And what this is doing is we had a weak reference to do this operation, but because we moved it from 0 to 1, we lost our weak reference because someone else could come along and need it. So we've transferred, in that process of going from 0 to 1, we transferred away our weak reference, but the spec says we should still have one. So we have to go and get one because someone has kind of raced with us. Basically, we're racing with someone, and we need to put back the weak reference that they hold. And if you don't do that, you have a problem. And it's basically this piece of code that's missing in the PLDI paper, and it was missing in our original implementation, and we found it with systematic testing. I did a proof after I did systematic testing. It's much better that way. So, does it work? Well, on the micro benchmark that shows exactly what I want to, yes. It is perfectly, well, other than going slow once you use concurrency, because that's kind of what happens with concurrency, after that it's flat, which is what you'd expect. There is obviously problems down the line, so there are worse cases. So because now going from strong 1 to closed is a 2-step operation, that means there's 2 atomic operations where previously there was 1. So what we find is if we do the exact worst benchmark, in fact the one that I really don't want to show anyone, but I put it on the side anyway, we get that we go almost half the speed because we're doing twice as much work. So then the question is, can we do better? Well, if we take the large algorithm collider and we take the state machines from the original code and the new code, and we add some more edges, and we glue the 2 things together, we get this big state machine. And if we do this big state machine, then we get a new algorithm out that doesn't have this problem. So then you can ask, can we verify this with Starling? Well, by this point of using Starling, I'd just kind of given up. And I was like, but I did talk to Ben Simner, who's one of the original authors of Starling. He's a student of Peter Sewell. I don't know if he's in the audience. I can't.
Not today.
Not today. No. Okay. So he went, I sort of challenged him with this when I was visiting the computer lab in Cambridge, and he went away and got distracted from writing his thesis, which is the best time to challenge anyone to anything, obviously. And he went and spent a couple of weeks getting it through Starling. So yes, you can get it through Starling, but it was very messy and horrible, but slightly less obviously than writing a thesis. So what's happened to that slide? There. Okay, so yeah, we have a paper at ISMM that goes through all the verification and the details, and you can find code, you can find more benchmarks and stuff. But I just go back to the things that I learned in Peter's office. So when I went there on the first occasion, I was doing Java verification. I didn't know about real pointers. I didn't want to touch concurrency or tool support. And by exposure through the wonderful, kind people in Peter's office, I now have a paper that does horrible pointers, concurrency, tool support, and it even has performance graphs in. So, questions?
Thank you for explaining how Peter ruined your life, Matt.
I mean, I'm quite amazed you've got this through Starling. First of all, I think that's an automatic tool. Now, you remember there's the Maged Michael work which showed that, what's the transactional memory? It sounded really good, but then there were cases where locking just beat it badly, right? Like, so you know this because you know about all these micro benchmarks. You can beat. If you consider Azure, do you reckon Azure's workloads will be a good fit for this, or is this something you would care to speculate on at all?
So my problem I have in terms of finding a good workload for this is I haven't managed to find anywhere that uses weak references in a concurrent setting where it is on the profiling trace. So this code is academically interesting. I have not found a practical industrial use for it.
Is that you couldn't prove that it was good, or that you think that you're not sure that where it would be?
I can't find anywhere where it will appear in a profile trace at the moment. So I've looked at a bunch of code, and if it's not in the profile, no matter how fast you make it, it doesn't matter, right?
Yeah.
So I haven't found anywhere where the promotion of weak to strong is a bottleneck in any way.
Okay.
Last quick question. I wonder if you have tried to verify the DOM tree manipulation with that, because, for example, in fast DOM algorithm in Internet Explorer and Edge, right, using both strong and weak references, maybe that's an application for this.
So the problem is also finding something that's highly concurrent using the weak reference promotion. So there are places where I'm optimistic if I can get good benchmarking infrastructure for them, but the problem is getting high quality profiling information out of someone else's code is a fairly large task. So the number of times I can do that before I give up is not that high. And I'm not writing a PhD at the moment, so I need to find someone.